Thank you. Hello, everyone. Thank you so much for having me. Thanks for the introduction. Uh, yeah, so I'll basically be taking you all to our 3 years journey of making MySQL or evolving MySQL into a type of a database which people used to use because they have no other choice, to a database now which sits at every single business critical application that Uber has. So no matter if you are booking a ride or like ordering something from Eats, MySQL sits at each of these business critical infrastructure. And what does it take to use something like MySQL to handle that kind of use cases? Um, so we'll quickly go over what is the current stack of MySQL looks at Uber. What are the challenges that we faced in building the stack? What are the optimizations and what kind of solutions we came up with to handle the scale? And what are we doing right now to basically evolve into the next step? Um, So before we go here, I want to give a very basic idea of what the scale looks like. This is just MySQL scale. And this is also around 6 months old. So we have almost 2,600 plus clusters. A cluster is a MySQL deployment with one leader and multiple replicas. In total, we have around 22,000 plus nodes. All of these nodes must be storing some exabytes of data. I don't have the exact data count, but we have clusters with individual nodes using almost 12 terabytes or even more. We don't like those, but they're there. One of the very important things, if you are serving a product stack in a company like Uber, which needs to be up every time, the most important thing that people track is your availability. Like you have to be there. Your database needs to be available at all the time, and the SLA that we give to our users is 4 nines of availabilities. What this means is that you can only tolerate 8 seconds of downtime per second, per day, 4 minutes per week, and around 52 minutes per year. So basically, you have to be available all the time. Now, when you are working with this scale and when you have this kind of requirements, and when you are so deep into the product stack, it is impossible to manage all of this via any manual operation, or you need a very reliable and resilient control plane or automations, which can not only do things on its own, but it should also be able to detect if there are any problems, and it should also be able to take corrective actions when those problems occur. Because if there is any manual intervention at any point in time, it will cause the delay, and it will basically end up making this nines lower. And so this is what I want to talk next. This is the architecture of the control plane, which makes this automation and which makes this stack possible. It is broadly divided into three categories: uh, data plane, control plane, and the discovery plane. Um, Data plane here, this is basically where the MySQL and the EnoDB and the RocksDB all lives. This is the pure storage engine layer. We use Percona's MySQL. There is nothing special there. But on top of it, it is being used by, it also contains, the data plane actually also contains a lot of helper modules and components, which does a lot of bookkeeping and other stuff. Like for example, you have the health prober, which is responsible for tracking the health of the MySQL node. I'll go over this component a little bit in detail in the next slides. Then we have the metrics container. This basically emits every possible observability that is possible to extract from a MySQL node. the backup, and this is basically disaster recovery, audit logging if you have any sort of compliance requirements for the database, and then CDC stuff. Um, the second component is the control plane. Now, this control plane is it basically is the brains of the entire operation. This anything that needs to be done to any of these MySQL clusters, it is the responsibility of this control plane. So it does it does the normal cluster operations. For example, if you want to take if you want to add a node to the existing cluster, or if you want to drain a node, if you want to do a leader election, if you want to do any consensus based grouping, etc. This is all being done by this manager. Um, this manager is not your typical microservice. This is still a stateless service written purely in Golang. But this is not a typical microservice in the sense that it's not a request response thing which we normally do. Because the things that the kind of operations that we run on these clusters, they are not like a quick thing. Like for example, if you are adding a node into an existing cluster, for a 1 terabyte node, we normally takes around 40 minutes of time. So it needs to do this one operation for 40 minutes. Disaster recovery could take even longer. Even the leader elections could take around 10 to 20 seconds. And these 10-20 seconds is actually an eternity in software world, because in this time anything can happen. Like your service can restart because it's a stateless service. It can restart, or a new deployment can happen. There are n number of things which can happen to a stateless service in 10-20 seconds. Forget about hours. So you need, so this manager needs a way to basically orchestrate these operations that it needs to do on the MySQL in a fault tolerant, and in a way there where if the operation that it is performing, if it fails at some step because of whatever reason, it should be able to know that where that failure happened, and it should be able to retry it on its own. That's like a very, very important component of making this entire system work in a self-serve fashion, because you cannot keep looking into the failures and keep doing stuff. For that, we use something called as cadence. So all the operations that we do on MySQL, whether it is leader election, whether it is uh, scaling, scale up, scale down, whatever you can imagine, a schema change, MySQL server variable operations, whatever you can imagine, all of this, we design this as something we call as workflows. These workflows are nothing but a series of steps that happens one after another. For example, a leader election can look like, what is the current leader, what is the health of the current leader, let stop the writes on the current leader, enable the writes on the new leader, make sure that the replication works, and then enable the writes to the customer. So all of these operations that we do is modeled as part of workflows, and each of these workflow has these steps. Cadence actually helps us manage or orchestrate these entire workflows, and it knows during a series of deployments, or during no matter how long the workflow is running, we literally have workflows which runs for days. No matter where the workflow is, it knows what is the state of the workflow, where it failed, and it can retry that failure again. This is, by the way, an open source technology, open sourced by Uber. And if you are in requirement of an orchestration service which needs to work at like billions of workflows per second scale, Cadence is the one that you should look into. So that's the operations part of it. The second thing that the control plane also does is the failure detection and recovery. So the control plane is designed in a way where it can detect that there are some problems with any one of these MySQL nodes based on the rules and based on the metrics that we have defined. And when this happens, it can take corrective actions on its own without requiring any manual intervention. If all of this works well, we do not even know, like we as in both the MySQL platform team as well as the customers who are using it, do not even know if there is anything wrong which has happened to the MySQL. It all like figures out and corrects it on its own. And the third part is the discovery plane. Discovery plane, a little bit about discovery plane. So Uber's infrastructure is very like diverse and heterogeneous. For example, we have our on-prem machines. We have multiple cloud providers, OCI, GCP, what have you. So, and we literally have no control over where these MySQL nodes gets placed into. What we do have a requirement is that every single MySQL cluster must be divided into 3 different failure domains. Normally, these failure domains are different data centers, so that even if there is a problem in one of the data center, our end-to-end business metrics are not impacted. Because it is so heterogeneous, it is not possible for the clients to keep track of where my MySQL nodes are. So this discovery service is the one which abstracts this entire topology from the customers. What customers get is just one IP, which is unique to the MySQL database, which never changes, and just 2 ports. One port is for the leader, and one port is for the replicas, in case they want to do the reads and writes. And the second operation that this routing plane does is it also load balances the read traffic within the replicas. One of the very important thing, and why we have a separate discovery plane for it, is we also try to maintain affinity between the microservice or between the call to the MySQL database, meaning that if, let's say, a service is running in a host in GCP, we try to send that query to a MySQL node which is running in GCP or some sort of Google hardware. Why? Because this cross data center latencies are, I would not say bad, but it's very unpredictable. You cannot give a very clear SLA between an OCI network and the GCP network. So this discovery plane actually tries to keep affinity between the source and the destination of these MySQL queries, keeping the load balancing in mind, so that it does not overload any particular node. So this is like a very broad description of how the control plane looks like and how do we use automation to do this stuff. Now, using this, what's like the problems that we have, how do we use this control plane to solve some of these problems at scale? And the problem that I have is leader election. So a typical MySQL cluster looks like this. We have a single primary MySQL. We have a single node which handles all the write traffic, and that gets replicated to the replica using standard MySQL binlog replications. Now, because there is a single primary node here, this is basically a single point of failure. In case this goes down, your entire write traffic is down, and you have availability loss. So the first problem is that because of this, there is a very, very high chance and keeping this single point of failure and adding it to the kind of diverse infrastructure that we have, because in total, I think there are like 300,000 hosts where these nodes could be placed. At any time, any one of these hosts can go into a maintenance. Anyone can take that host out of their serving stack and can apply a kernel patch, or it could be because of customer queries as well. If, let's say, there is a surge in writes that came to MySQL, which it did not able to handle, this can actually go down. So there are a lot of ways, either it is infrastructure or it is customer driven, where this particular thing can go down and cause availability loss. The second thing is doing a primary failover itself is not an easy process in MySQL, because you have to, it involves a lot of steps. Like, for example, you have to select a node which is most caught up so that you don't have data loss. It has to be in the same region as the old primary, because since it is a single primary, it can exist in one place, either it is in GCP or OCI or wherever. And if we promote a different node, the clients might start getting a different latency for their writes, which we don't want. So a primary failover the primary failover or the leader election itself is a process in MySQL, and we want to reduce it as low as possible. The second thing is the other thing is it also needs very extensible observability. Like you need to know what my leader node is doing, and if it is down, you almost need to know immediately so that you can take corrective action and you can reduce the number of seconds that you need to make it up again. And all of this actually requires a control plane that we looked into, which can handle this well. So how do we use this to manage leader election? Is something like this. So this is just one example. I'll also go over some other. So let's say there is this leader here which is handling all the rights. We have a health checker which runs in the same host as the MySQL leader is running. What we saw in the architecture diagram, which is this. So the health checker actually keeps on pinging MySQL. It is not a just simple ping. The checks that it is doing are quite extensive. For example, if it is a leader node, it also looks into some MySQL variables. It can also look into its CPU or memory usage. And of course, if it can accept new connections. And it maintains a log of all of this into a separate log file. Now, one question here is that why does it have to maintain a log here? Because this is the guy who knows that if there is a failure, why can't this guy itself take a corrective action directly into MySQL? The reason for that is these two, the leader node and the health checker, actually they are running in the same, let's say, container. So this guy does not actually have the full picture of how this leader node is looking from an external client's perspective. What that means is that this health checker does not measure the availability from client's perspective, which is very important, because how the MySQL node, because the leader could be active and it could be running correctly, but there could be a network isolation between the leader node, the host where the leader is running, and the client microservice. And then you don't, even though the health checker says that the leader is healthy, but the client is still not able to connect. So one of the very important requirement that we had here is that all the availability metrics, etc., that we see, it has to be from the client's perspective. It doesn't matter how your MySQL node is running. If the client is not able to connect it, you are down. So it cannot take any corrective action. It has to be done by someone external which works in the same domain as the clients. So it just writes these failure logs to a file. And then we have that part of the control plane which is called as controller. This actually reads this logs files, and the controller does not immediately take action because it could be a false alarm as well. So we have the controller is designed in a way that whatever signals that it gets, it tries to soak it for some time. In case of leader election, it is I think 5 seconds. But it tries to soak it for some time, and once it realizes that the signal that I'm getting is stable and there is a real problem here, it actually invokes a leader election in the MySQL cluster. So this is how the data plane, the control plane, and actual MySQL all comes together to perform this automated failure detection and mitigation. Another example that we have for here is because we have the replication between leaders and replicas, and the replicas can actually lag for whatever reason. The replication SLA that we have is 5 seconds, but so we can also do a similar thing for replication lag. What we can do is this health checker, or it could be a different module. It could be the controller himself. It can ping the replicas as well, tries to find out how much lag does a replica have. And if it finds out that there are some replicas which is breaching the SLA or which has lagged more than 5 seconds, it can actually take it out of the traffic so that the client does not get any stale data. That is another automation that we have. Again, happens on its own. It adds, it removes, and then when the lags comes back, it again adds it back. And it also makes sure that when I'm removing nodes, I should not reduce the cluster capacity by a lot so that the clients do not, so that the MySQL does not have enough capacity to handle the load. Um, the another automation that we have is consensus based. So we also have 3-node consensus system in MySQL for clients which needs even higher availability. For example, if you are in finance, or if there are some services which are in trip serving which cannot take downtime of even 4 seconds. What we do is those clusters are in a consensus group, so that so that the leader election that we have to do, this part is external. So the controller does a leader election in MySQL clusters. This takes 1 or 2 seconds. If there are clients which cannot even which do not even want that, we do a consensus based leader election, because that happens inside the MySQL group itself, so it's very fast. But it needs that there should be 3 nodes in the consensus. These 3 nodes needs to be in different failure domains, so that if there is one entire data center down, you still do not lose consensus. So again, it has a lot of steps. It has a lot of validations that we have to do to maintain the consensus. This is all again done by the controller. It looks into the cluster state. It tries to identify what it has to be done. It looks into all the signals, and if it finds out that there is something that there is some action that needs to be taken, the control plane or the controller and the controller does that. So that's how detection and mitigation works in a very broad fashion. This I will skip. So actually, fine. So this is what we were looking into, right? So there is one leader. There are multiple replicas. The availability is good with this. This model we ran till early 2024. This made MySQL. This improved our availability. This made MySQL famous at Uber, that it can handle business critical features. So we started to get more and more use cases, and some of these use cases start to push that single leader architecture. So the problem is with single leader is that's a single point of failure. It's a single node which handles all the writes, and you can only scale a node to a certain limit. We at Uber we have this hard limit of we cannot go for more than 48 cores on a single node, and this is 300 GB. This is incorrect now. So 48 cores and 300 GB, you cannot ask for a bigger node than this, because it makes placement a little bit harder. So you have to work under this limit. This 2 terabyte limit is not a hard limit, but we try to keep it under 2 terabytes, because if it goes to more than 2 terabyte, every single operation that you have to do, for example, schema change, backup restore, etc., all becomes expensive and time consuming. So we have these limitations with which we have to work on, and all of this, when these high scale, high throughputs, when we started onboarding these high scale and high throughput systems, we started to breach all of these requirements very, very quickly. So the leader, even though we have all the safeguards, because of the sheer ingestion load, the leader was going down. The CPU bottleneck, because it only can operate with 48 cores, that's also started breaking. And in reality, we actually did not had 48 cores. As soon as the CPU starts, what we observed is as soon as the CPU starts to go to like 60% or even 70%, the cores itself starts to throttle, and you start to see degradation even at 60 or 70%. And there are I/O challenges. There is only a limited amount of I/O bandwidth that is given to each host. And the second thing is, since there is a single leader, you can add replicas as much as you can, but every single replica adds a little bit of overhead to the leader for that replication. So there is also a limit on how many replicas that you can add. That limit is huge. MySQL replication is very, very effective. It's like very performant. There's nothing in software industry which is as performant as MySQL replication. But there is still a limit. You still need adds. So there's a clear need of getting away from this single leader architecture if you want to onboard more of these high throughput systems or high demanding systems like this strip serving or even Uber Eats. So we did not had the capability to provide MySQL sharding out of the box because providing a platform capability for MySQL sharding is hard, and we needed to we needed to improve our control plane for that. So we first came up with this intermediate application level sharding scheme. What we did is we still had multiple MySQL clusters. These are still independent clusters. But they all had same schema. They had different users, and our control plane actually binds them together. What this means is that when you do a schema change, let's say you issue a schema change operation, the control plane knew that this is part of a single shard cluster. Even though these are different MySQL cluster, they didn't even know about each other, but our control plane knew that these are part of some group. And when it performs this operation, it used to perform in all of these 5 operations. So we built a sharding scheme from an external point of view. And that also went to client. So we gave client this customized client where they can specify these shards as config and the sharding scheme to it. And this client then, based on the query that is coming to it, can identify which shard which MySQL cluster this query or this row should go to, and then sends the query to that particular shard. It worked, but it made our entire operation very, very complex. Because as you can imagine, if you want to do, like, let's say 3 shards are fine, but many of these use cases have 10 shards, even 30 shards. Now, if you want to do a schema change operation, you have to do it 30 times. If you want to create a user, you have to create 30 users. And the worst part of it is that the clients are actually aware about the sharding, because they need to provide that information in their own config file. So resharding is almost impossible without asking the clients to do the changes on their end, which is the worst part of it. We had this intermediates set up for around 6 months till we built or till we started using or we started thinking about providing this MySQL sharding as part of a platform capability. We did not wanted to reinvent the wheel. So we started looking into open source options. What do we have, and how do we use it inside Uber's infrastructure? We chose Vitess. Vitess is an open source. Vitess basically gives you a routing layer on top of MySQL, where it has a proxy. It knows about your shards, it knows about your schema, it knows about your sharding scheme. And the best part about this is that you can connect to Vitess like you can connect to a MySQL database using the same TCP MySQL protocol. So the clients do not know that how many shards I have, because they connect to a single proxy like they connect to a MySQL database, and the proxy used to take care of where to send this information, how many shards I have. If you want to issue a schema change, you can issue that to that proxy, and then proxy will distribute that in an incremental fashion. So what we built here, we found that all of that and even more is already present in Vitess. So if you are looking for a sharded MySQL use case, you can actually explore Vitess. Now, it came with its own challenges. Vitess is not it's not designed to build multiple, it is not designed to work with having clusters with a lot of replicas. We have clusters they recommend 3 replicas. We are running with 30 replicas. So we have to made a lot of changes in top of Vitess to improve its availability, to improve its resharding capabilities. We are also pushing that to open source. But yeah, we ended up using Vitess. It's working well. One of the highest use cases that we have runs on Vitess. It has around 5 to 7 million QPS consistently, and it's serving well. This is how the architecture looks like. This is the proxy that I was talking about. Applications connect to this like a single MySQL database, and it takes care of distributing the load to multiple shards and everything. The most important feature why we chose Vitess is that it completely abstracts its sharding concept from the applications. The applications do not know how many shards I have, and what else. It basically gets abstracted everywhere, and that gives us a lot of flexibility here. This is what we talked about. So I think that's all I have. And yeah, I'm free to take any questions.
Hi. I just wanted to know why you guys decide to go for leader election as compared to a hot standby for MySQL. Because with a hot standby, we would like be able to choose okay, my primary master is not working. I can just immediately switch to the hot standby.
In case of hot standby also, you have to designate a leader into the cluster which can handle all the write. So even in case of hot standby, you have to promote that hot standby to leader, so that that hot standby start accepting reads. We actually do have a hot standby kind of concept where we have some replicas which are which are more consistent, which basically acts the rights to the leader, and we tend to promote those. But it still needs an election. The standby still needs to be promoted to leader so that they can start accepting rights. Standbys do not accept rights, they just acknowledges the rights to the leader, so that when the leader goes down, we have at least some replicas which has all the data which can be promoted